So we're on to section 11.8 from our book Stewart Calculus. For those of you just turning in, this is a series of lectures I'm making for my Calc II class. We're towards the end of the semester, so if you haven't been sitting in on Calc II with me all semester, you may not follow this too well. But we're on to power series. We had just spent some time talking about infinite series. And when they converge and when they don't converge. And power series are series that can be thought of as functions. In particular, we think of it as an infinite polynomial. So let's look here. A power series, and let's start with a power series expanded about 0, is a series of the form a n x to the n. So a n x to the n, a sub n being a constant, x being a variable. Okay, so a variable that might change. And the key question is when do these power series converge? The domain of this is going to be a function of x where that converges. So the domain of such a function is going to be the set of x for which it converges. And that's what we're going to be looking for. But let me just point out, so this is your generic power series starting at n equals 0. And notice when n equals 0, x to 0 is 1. So I get a0. When n equals 1, I get a1x. When n equals 2, I get a2x squared, and so on down the road, a cubed, 3x cubed. Notice that it's just like an infinite polynomial, right? A polynomial of degree infinity, assuming that it doesn't end up in all zeros. That's what's so useful about them. If you think about it, what are the things that are easiest to differentiate and integrate? Yeah, you got it, polynomials. That's what we're going to be working with. Okay, so here's some example of power series, just to expand these. X to the n is, when I expand, that's 1 plus x squared plus x cubed plus dot, 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 dot. X to the 2n, of course, starting at n equals 0. That's to the 0, that's 1 plus 1/2 x, right? X to the n over 2 to the n, sorry. 2 to the squared is 1/4, so 1/4 x squared. 2 cubed is 8, so that's 1/8 x cubed, and so on. And of course, this last one here is a power series that's going to be when n equals 1. Notice I'm starting at 1 here, partly because I can't divide by 0, right? When n equals 1, I have 2x plus when n equals 2, I have 4 over 2 squared, which is 4, so that's just 1x squared. When n equals 3, I get 8x cubed over 9, right? 8x cubed over 9, and let's do one more. When n equals 4, I get 16 over, that simplifies to 1x to the 4th, and so on down the road. So the idea here is those are all power series. Power series expanded about 0, and we'll talk about what that means in a different lecture. Now, a few things to note here is, again, we're looking for the domain in which this converges, right? And let's stop here for a moment and notice that there's 2 here that I can sort of determine the domain in which it converges right off the bat. First, let's write this in Greek. Let me notice that this third one here can be rewritten as the sum n equals 0 to infinity of x over 2 to the n. So notice that these are like geometric series. Both of these, this one and this one, are geometric series. And we know that when geometric series converges, well, in this first one, r is equal to what? R is equal to x. In the second one, r is equal to x over 2, right? So it converges when the absolute value of r is less than 1. So for this first series up here, it's going to converge when absolute value of x is less than 1. Otherwise, it diverges, and it converges to 1 over 1 minus r, 1 over 1 minus x. In the second one, it's going to converge when absolute value of x over 2 is less than 1, and that's going to converge to 1 over 1 minus x over 2. Okay, so what does this mean to us? Well, uh, what this is saying is that this function, the function that's determined by this power series, is equal to this function, the function 1 over 1 minus x, as long as the absolute value of x is less than 1. The absolute value of x being less than 1 is the same as being on the interval from -1 to 1, right? This is an interval from -1 to 1. As long as I'm restricting myself to this domain, these are the same functions. The power series is equal to the function 1 over 1 minus x. Meaning, like, for instance, if I plug in a 1/2 over here, I get the same thing as if I plug a 1/2 into the power series. It converges to the same thing, which would be 1 over 1, 2. It would converge to 2. Okay, and finally, the second one also, this power series is the same function as 1 over 1 minus x over 2, as long as the absolute value of x over 2 is less than 1. That means that's the same as -2 less than x less than 2, right? If we solve for that, or x being in the interval from -2 to 2. So the idea being is that this function 1 over 1 minus x over 2 is equal to this function, this power series, as long as x is in this interval. So if I restrict the domain to that interval, they are equal functions. Okay, now this bottom one we need more work with, because this bottom one is not a geometric series, right? Because of that n squared, it's not a geometric series, so I can't use geometric series argument to talk about when it converges and when it doesn't. And it's going to be a lot harder to figure out what function it converges to. And this top one is just a generic power series. We really can't say much about that because we don't know what the ANs are. So let's get some of the stuff we already know about out of the way. Okay, one second. Okay, so we've got these examples reorganized a little bit. Notice that I rewrote the two power series, geometric series examples that we had just gone over up here, and we're going to look at this one. And the goal here is to figure out the domain of this function, meaning what x values does this power series converge? And this is not a geometric series because of that n squared, like we mentioned before. So we've got to use some other tests to determine convergence. And you'll find for power series, the ratio and occasionally the root tests are really nice to try. So let's try the ratio test here. So if we look at the ratio test, this is going to allow us to get some bounds on what we're looking at. So if I look here, ratio test, I'm going to look at the limit as n goes to infinity of the absolute value of 2 to the n plus 1, x to the n plus 1, over n plus 1 squared, all over 2 to the n, x to the n, over n squared. Those absolute values down more. And that simplifies to the limit as n goes to infinity. Invert and multiply, and the only things that might be negative here are the x's. So I'm going to bring the absolute values to the x's, and we get 2 to the n plus 1, sorry, 2 to the n plus 1, n squared, times absolute value of x to the n plus 1, over 2 to the n plus 1 squared, absolute value x to the n. And that's going to be the limit as n goes to infinity of, notice the 2 to the n plus 1 divided by 2 to the n is just 2, right? Absolute of x to the n plus 1 divided by absolute of x to the n is just absolute of x. And then I've got times n squared over n plus 1 squared, the quantity squared. And notice that this n squared over n plus 1, the quantity squared, is a rational function, right? The numerator and the denominator are polynomials, and both are degree 2. They're both squared. So that's going to just go to 1. So this whole limit's going to be 2 absolute value x. So if you recall, with the ratio test, what we're checking is to see whether this limit is less than 1 or bigger than 1. If, let's do a different color here. If that limit is strictly less than 1, then what do we know about the series? Then it converges absolutely, right? Absolutely. If this here is strictly bigger than 1, what do we know? Then it diverges, right? The issue is what happens at 1. We still have a little bit to say, but right now what we know is the domain of the function is one of 2 things. So 2 absolute x being less than 1 is the same as absolute x being less than 1/2, right? Or negative 1/2 being less than x being less than 1/2. That's the same thing. So we know one of that the domain of this function is either the open interval from negative 1/2 to 1/2, the closed interval, including both endpoints, or one of the half-open intervals, right? Or the one including the left endpoint but not the right, or the right endpoint but not the left. Right? It's one of those 4 things because it converges for everything between negative 1/2 and 1/2. It diverges for everything bigger than 1/2 or less than negative 1/2, but we don't know what's happening at 1/2 and negative 1/2. So for that, we're going to have to use another, we're going to have to test separately. So let's make these things smaller and then test those separately. Okay, so now that we've got a little bit more room, let's look and see what's happening at the 2 endpoints of this interval. Okay, so at x equals negative 1/2, well, let's go back to the original series. The original series is this thing up here, right? We're going to have the sum n equals 1 to infinity of 2 to the n. X is negative 1/2, right? So that's negative 1/2 to the n over n squared. And that is, well, negative 1/2 to the n can be rewritten as negative 1 to the n times 1 over 2 to the n, right? All over n squared. And you notice the 2 to the n's cancel, so I get this is the sum n equals 1 to infinity of negative 1 to the n over n squared, and that converges, right? This converges. And that's the alternating series test that gives us that converges. Or you may notice it converges absolutely because 1 over n squared converges. We'll get that in the next one. So let's see, x equals 1/2 gives us what? We're looking at the sum, n equals 1 to infinity of 2 to the n times 1/2 to the n. Of course, 2 to the n and 1/2 to the n cancel over n squared. So that's the sum, n equals 1 to infinity of 1 over n squared, and that converges y? P series, yes. Converges P series with P equal to 2, which is bigger than 1. Okay, so it converges at both endpoints. That means the domain of this function, the set on which this series converges, is negative 1/2 to 1/2, the closed interval. So this is, the domain is negative 1/2 to 1/2. Of course, as we noted in the previous sections, in general, it's really hard to figure out what it converges to, so we're going to save that for another section. And there's going to be some we may not even know what it converges to, okay, as a closed form of the function, as anything but a power series. But this is a good place to stop this video.